Bung Viko, Pak Robert nggak ikut?
Pak Robert hari ini kebetulan ada mungkin sebenarnya doa Pak. Jadi, izin karena beliau sama seperti Bapak.
Prof. Edi, kapan-kapan lagi Prof. Edi?
Iya, kangen ya, Pak Beda.
Jarak jauh jadi. Dari ke Bandung, dari bisa ke Ambon.
Betul ya.
Ini Prof. Joko kemarin mau datang.
Selamat sore.
Iya. Sama saya harusnya, tapi batal dua-duanya.
Iya Pak, saya ketemu di Hotel Century, kita bilang mau Ambon.
Pak Viko, sudah bisa kita mulai?
Pak.
Oke, baik, nanti mungkin kalau pada waktu pelaksanaan mic atau Pak Rektor, mungkin saya pindahkan dulu ke hostnya ke Pak Rektor maupun ke Mike KCD.
Adik-adik dongjang itu ya, sudah itu.
Ada Ibu Wilma.
Baik, kita mulai Bapak dan Ibu.
Silakan.
Ya. Good evening everyone. Good afternoon from Bandung and also good morning in the UK, especially for Mike. All the participants, thank you very much for your coming and also to join with this guest lecture organized by University of Patimura and supported by Institute Technology Bandung. His Excellency Professor Dr. Martinus Johannes Septano, SH MPum, Director University of Patimura. His Excellency Vice Rector of Academic Affairs, Professor Freddy Lewa Kabesi. His Excellency Vice Rector of General Affairs, Dr. Yance Cipta Budi. His Excellency Vice Rector of Planning, Cooperation and Information System, Dr. Muspida. His Excellency Dr. Mike Cassidy from University of Oxford. Thank you for your time. His Excellency lecturer from Unpati and also from ITB and our value student. Before we start the guest lecture by Mike Cassidy, let me to read the agenda for this evening. Okay, this is our agenda. Welcoming remark. My name is Mirza. I will be your moderator and MC, our master of ceremony for this session. And then after that, we have opening speech by the Director of University of Patimura, Director already here. And then we have guest lecture from Michael Cassidy, University of Oxford. After that, we have question and answer. And then before we close the session, we have a photo session together, and then also we have closing remark will be delivered by Rector of University of Patimura. I think at the first, we will give the opportunity to our Rector, Professor
Thank you very much, moderator. And dear Dr. Michael Cassidy from Department of Earth Science, University of Oxford, United Kingdom. Dear Professor Dr. Eddie, Dr. Misram Abdul Rahman from Biological Engineering Department, Institute of Technology Bandung, lecturer and student from Biological Engineering Department, Patimura University. Good afternoon from Ambon. We're all welcome to the guest lecture through webinar session under the theme Explosive or Effusive, investigating the factor controlling volcano explosivity in the pandemic COVID-19. Dear audience, Maluku, which geographically surrounded by ocean and enormous number of islands, creating a new world full of natural resources in its ocean and land, considered as natural laboratory needed to be preserved and developed. The situation led Patimura University of known as UNPATI as a public higher education in Maluku to be responsible for maintain and manage the research of the natural resources in Maluku. To answer the challenge, UNPATI has set two main goals to as Bina Mulia Kelautan. It means that UNPATI will maintain and manage the development of Maluku not only from its landscape, but also in its seascape, based on the geographical condition. This continue and sustainable development need to be done. Dear guests, our audience, the richness of Maluku ecosystem of supported by the geographic condition where Maluku is in the ring of fire. Then the knowledge about the volcano in becoming special needs of Maluku people, which becoming a new challenge at the Patimura University by initiation with the Institute of Technology Bandung in partnership with the University of Oxford by accompanying this guest lecture as the answer to the challenge. Dear audience, I do believe that this seminar will help us to increase our knowledge and answer awareness about the potential and the risks as Maluku people who live as the part of ring of fire. Also, I do hope that this cooperation could be a trigger for all of us to have more collaboration both with Institute of Technology Bandung and Patimura University and Oxford University in the future. To the lecturer and students of Biological Engineering Department, I hope this lecture will be knowledge sharing session to enhance quality and understanding to biological engineering science, and of course, I hope that this event could support accreditation of study program as well as accreditation of Patimura University. Dear audience, last but not least, I wish this fruitful guest lecture will bring benefit to all of us and maintains and manage our environment for better life. I wish you all very informative and enjoy session. And please check our warm greetings. Automation, drive and challenge. Good morning for you, Michael, in the United Kingdom, and thank you very much for your meeting with us in Patimura University. Thank you.
Thank you very much, Pak Rector, for your
Michael, I hope
speech.
maybe the next time you come from to England to Maluku, because we have many islands and very nice if you live in Ambon for 1 month, or up to you.
Thank you very much.
I agree with that.
Happy for you.
Thank you very much, Pak. Yeah. Thank you very much, Pak Rector, for your opening speech. And then our value guest, before we start the discussion or because of the talk from Mike Cassidy, let me to introduce him. I will read the short bibliography about Michael Cassidy. He got BSc from University of Bristol in 2006. At the same year, he became the volunteer research assistant in the University of Colima and UNAM Mexico. And then 2007 and 2008, he got MSc from volcanology and geological hazard, Lancaster University. And then 1 year later, he continued for PhD. And 2012, he got a PhD degree from Ocean and Earth Science University of Stanton. And recently, he became NERD's Independent Research Fellow, University of Oxford. Okay, Mike Cassidy, time is yours.
Thank you. Yeah, thank you very much. And thank you very much, Mirzam, and thank you very much, Paksata, for all the lovely introductions. I'll just share my screen to see if this will work.
Okay.
Oh, can you enable my screen,
Yeah.
Mirzam?
Yes. Okay, please wait.
And selamat siang to everyone.
Sorry.
Yeah.
Wait a moment. It's not. Is it work?
Yeah, that works. Perfect.
Okay.
Okay, can you see my screen?
Sure.
Yes.
Yes, perfect.
Excellent, excellent, brilliant. Well, it's really nice to, it's a great privilege for me to give this talk, being so many thousands of miles away, and it's a really nice opportunity to do so. Yeah, it's really nice for you to set this up, and I hope that you can learn something, and please have some questions if you want to ask me any questions. I'm familiar with some with the volcanoes in Indonesia, but not so much on that kind of eastern part of the arc. So that's really interesting, Banda Api and in Malacca, etc. So that's really interesting. But this talk is going to be general about explosive or effusive eruptions. And the last few years, I have been investigating all the different factors that may control explosivity and how a volcano erupts with different styles. And you can see in this picture over here, an explosive and also an effusive eruption. This one is from the Soufrière Hills volcano in Montserrat in the Caribbean. And this one is from Kelut in East Java, which I'll talk about a bit later. So I first got into volcanology when I was about 14 years old. I thought I'd just give a very brief background. I was expecting all volcanoes that you see on the TV, at least in the UK, to be boiling kind of red lava pots, like lava lakes that you see in Hawaii and things like that. But actually, I looked on the TV one day and I saw this particular clip, which is based in Sufra Hills in the Caribbean. So that's just a short clip, but it really kind of made me think twice about what volcanoes were, that they weren't just these kind of bubbling lava flows that flowed gently down the slope, but there were these very big, very explosive, potentially dangerous eruptions with these pyroclastic clouds and things that could devastate regions like this one in Montserrat. So seeing that when I was age 14, I ended up doing my PhD on that volcano in Montserrat, and I even met the person who took this footage, and he showed me around the destroyed city that the people used to live in. So that's kind of story goes full circle, which is quite interesting. Well, how I become a volcanologist? Well, I first I didn't like science subjects when I was younger. I didn't think I was very good at age 14, but then I ended up having a passion for volcanoes and for natural hazards. I did A-levels in science, chemistry, geography and geology. And then after school, I went to university and I spent about 7 years there. So 3 of those years, as Mirzam was saying, were in Bristol, training to do my undergrad. Then I did a master's and a doctorate. I was made to do lots of different classes, including maths and physics. And this was really important as well, because I feel like it gave me a basis to understand all the different parts of volcanology as well. And I've moved around a lot in 3 different countries, Mexico and Germany, and also in the UK, where I spent most of my career. And I've been to 7 different universities. So I feel like that's given me kind of a fair bit of experience, and it's great to work with people in different countries as well as countries that I've been to visit, like Indonesia, and working with Mirzam. So I guess 7 years sounds like a lot of time to be spending in education and university, but it really didn't seem like a long time because I really enjoyed it. I made lots of friends, I traveled and gained a lot of knowledge, for example, learning different languages like Spanish and German and things like that. So I would really encourage the younger people listening to this to really kind of get involved in your education and taking geology further if you can, and kind of enjoying all those experiences. So we talk about effusive eruptions. I'm going to talk to you exactly about what this is, kind of sometimes called flow eruptions. So here's a clip from Hawaii in the USA showing kind of a typical effusive eruption. This is kind of a slow moving lava flow. This is basaltic composition, as you well know. This is it going through a gate. These are eruptions a few years ago. So that's just a clip from America showing what an effusive eruption is. These are normally kind of low viscosity, so we're talking basaltic compositions, but as I'll talk about later, you can have effusive eruptions from very silicic compositions. So compositions that could be rhyolite, dacite, higher silica conditions as well. And we'll talk about why and the factors where you can have effusive eruptions as well. I also want to talk about explosive eruptions. Now, explosive eruptions And this is going to show you a clip from Chile in a few years ago with the eruption of Calbuco in Chile. And this is where that magma, that lava, is exploded, fragmented into lots of millions and millions of different particles called ash, and that gets blown into the sky, into the atmosphere, and that can spread thousands of kilometers away up into the upper atmosphere and create lots of different hazards like those pyroclastic flows that we saw in that first clip. So whereas effusive eruptions normally have fairly localized impacts, effusive eruptions, lava flow eruptions sometimes have a very localized impact. Explosive eruptions can obviously have a huge impact to a wider region, perhaps, between countries as well. So I guess there's a problem in volcanology at the moment. We're getting very good at monitoring volcanoes. We can monitor their seismicity. We can even now, we're starting to measure their deformation, how they can deform from satellites. And we can also look to see, so they can see how they deform, they can inflate, they can deflate. We can also measure their gases using sulfur dioxide cameras and UV spectrometers. This can give us an indication of potentially of how magmas can arise to the surface and whether there's going to be an eruption. Let me just, and whether there's going to be eruption. So the problem is, I guess we can normally tell if and sometimes when an eruption will occur, but we're still far from forecasting what style of eruption will occur. Will that be explosive, as we saw in that last clip, that can have a huge impact to the populations far and wide? Or could it be an effusive eruption that generally have a smaller impact and an effect on the population? So to understand this problem, to get better at it, we really need to understand the factors that control whether we're having an explosive and effusive eruption. So that's what I'll talk about briefly today. Here's just a graph to start off with, and this is on the left-hand side here, the y-axis, looking at lots of different eruptions through history, Bishop Tuff to Kelut to Vesuvius, Pinatubo. And then on the x-axis here is the time, and this is time before eruption. So on this right-hand side, we have the eruption. On the left-hand side, we have years, years before the eruption. And what I'm going to plot now is essentially how long it takes for that magma to ascend. So we can get that from magma ascent rates that we can compile, and also an idea of what depth they originated from, whether it be 4 kilometers, 5 kilometers underneath the reservoir, the magma reservoir. And what we can do, this gives us an idea of how long it takes the magma to ascend. In the red bars, I'm talking about effusive eruptions, and in the black bars, which I'll plot in a second, are explosive eruptions. And I'm also going to plot on, for the eruptions that we know about, so Pinatubo and the modern eruptions, when the onset of unrest, when we started seeing some sort of seismic deformation or some sort of activity. So here you can see the different bars that come up here now, and you can see that the effusive eruptions in red generally take much longer for the magma to ascend before eruptions. So we're talking months, weeks, even years sometimes. Whereas the explosive eruptions, the ones in black, they take about kind of in the order of days, hours, or minutes to ascend from the magma reservoir. So unrest that we see at the surface, we know that it's the unrest or the seismicity and things like that. They're not always associated with magma that's moving from the magma reservoir to the surface. So that's something to say, because, and we can say that because we see the onset of unrest, these green dots over here, are almost always dissociated from the time that the magma takes to ascend. So if they were coupled together, like in this instance here, then we can say that the magma is perhaps the cause, the magma moving is perhaps the cause for the seismicity or the unrest, deformation, gas, etc. And that perhaps is the case for the Kelut in 2007 eruption as well. So as I said, explosive eruptions ascend faster. On average, using this compilation, we're talking about 10 hours, and they often have shorter unrest periods. So there's less warning for explosive eruptions, on average about 220 days. The effusive eruptions, however, take much longer times to ascend. So they, about 98 days is the average from magma source, magma reservoir to the surface. And they generally have more warning. So there's more indicators of seismicity, deformation, gas, etc. Than explosive eruptions. So generally over a year of warning. So when we did a compilation of more recent eruptions, so all the VI4 eruptions, so that's the volcanic explosivity index above a certain level. So with these explosive eruptions since the 1990s, more than half, so 52% of these, show less than 30 days of unrest. So often these explosive eruptions have less than a month of warning. And it shows us that some, not all, but some explosive eruptions come with little warning. So this is something that we need to be aware of. It's not something that's the right way around, unfortunately. We'd like to have more warning for effusive eruptions, but it seems like explosive eruptions come with less warning, mostly. So when looking into the factors controlling eruptive style, and this is important because we need to get ahead of this problem and need to understand this, we made a compilation of all the different factors, and I'm not going to read these all out, but you can have a look at those in that paper there. And it's a good reference table if you want to get into this subject a bit more. So in that left-hand column, I look at the properties and the parameters that could be controlling eruptive style, things like the magma ascent rate, the magma viscosity, the bubble content, etc. I look at what controls those particular parameters or properties. And then in this column, I look at how those properties affect the eruptive style. And I provide numbers and also references if you want to look at those particular studies in more detail. So there's what you can see here, there's lots of different factors, and also they're very much interrelated, which I'll talk about in a second. So things like temperature, which are intrinsic to the magma. In other words, they are occur within the magma reservoir. Those can affect lots of different other factors like viscosity or bubble nucleation. Whereas some factors are external or extrinsic to the magma, things like the conduit and the vent geometry. And also a lot of these eruptive style controls don't just occur in the deep system, but they occur right throughout the whole magmatic system. So they occur within the magma reservoir, but also, and especially for dome eruptions and volcanic eruptions, there's a lot of control in this conduit region as the magma transits from the magma reservoir to the surface. And we can also see that processes that occur at the surface of the volcanoes, things like collapses, either through a dome collapse or a flank collapse, like in Mount St. Helens, can affect the deeper system and set off different controls that may affect the eruptive style. So one of the big factors that I'm sure you've heard about before is viscosity. And this certainly affects the magma explosivity. So this is an ability for a substance to resist flow, and you can see this video is a very mesmerizing video. You can get an idea of a slightly more viscous fluid than, say, water. And viscosity, so high viscosity would be very sticky, would be slow to flow, and low viscosity would be very runny, like honey, like you just saw. They're controlled by different things. One thing is chemical composition. We can also have a control of temperature and also crystals and bubbles as well. So in terms of chemical composition, You can find that high silica magma, so we're talking rhyolite, dacite, and things like that. Some things we have in, say, Krakatoa volcano, Rinjani volcano, similar to those. Because those silica, they have lots of silica, and those silica tetrahedra form these strong bonds and these strong chains. Those are called polymerized, and those resist flow. And that means that they make it harder for the magma to flow. And that makes it more sticky. And the reason why that has an effect on the explosivity is because explosive eruptions are driven by gas, by dissolved volatiles or dissolved gases within the magma. And if those gases can be released prior to eruption, then it will lessen the explosivity of the eruption. So with this example here on the right is a basaltic magma, and this has less silica, and this means that it's able to flow much more easily, and this means that gases are much more likely to be released because they can be released from the system, which is low viscosity. If you change the temperature of the magma, then this can also change its viscosity too. And if you have lots of crystals, they can get in the way, they can inhibit or they can make the magma more viscous and hold in those volatiles too, which we'll talk about a bit later. The other reason why high viscosity magmas can make more explosive eruptions generally is because they can fragment much more easily into ash. They can break up into more millions of different pieces more easily than a very low viscosity magma, which will just end up flowing. So here's an example. Here's a graph showing the viscosity on the left here from low viscosity, so your basaltic magmas, to your high viscosity, so your rhyolite magmas, more silica rich, a higher temperature as well. And here we have on the y-axis the strain rate. So this could be slow strain rate. So in other words, it could be a slow magma ascent, or it could be if you flow something very slowly, versus a fast strain rate, which is where you kind of pull something. Imagine pulling a liquid or pulling a solid very quickly, like Play-Doh or plasticine. So in a low viscosity magma, it takes a very, very high strain rate in order to break the magma. Whereas for a high viscosity magma, you need less of a magma ascent rate, or you need lower strain rates in order to cross this transition into glass. And that crossing the transition into glass is fragmentation. And that is where we have explosion of magma, which is liquid, into ash, which is these broken up bits of glass. But what we can say is that sometimes we can have the same magma composition. So let's say we have an andesite or a basaltic andesite, very common in Indonesia. We can have the same amount of dissolved gases. So the amount of gases in the magma doesn't always seem to matter. And the similar viscosities, but in fact, we can have different eruptive styles. So this is really confusing. And we were looking at to see why this could be the case. Even we have the same magma composition, the same dissolved gases, we have completely different eruptive styles. So what we did is we compiled different things together. We compiled lots of different ascent rates in together, looking at the magma ascent rate, so how fast it ascends from the magma reservoir to the surface, and looking at lots of different volcanoes. And this is different eruptions you can see down here on the x-axis. And this is a log of the ascent rate axis. And here you can see different viscosities, different compositions of magma. And what we can see is that explosive eruptions are generally at higher magma ascent rates, in contrast to the effusive eruptions, which are in red, are at lower magma ascent rates. And this is really interesting. It shows that, in fact, even if you have the same magma composition, say andesite, the same composition of dissolved gases, you can have really different volcanic eruptive styles. It can be effusive down here, or it can be explosive. And this seems to be very much dependent on how fast the magma takes to ascend. So these different symbols, this is in my paper over here, but these different symbols reflect how those estimates of ascent rate are being calculated. And you can see actually from this gray dotted line that divides effusive versus explosive, that it's not a very clear line. It's not a very clear division of particular ascent rates, but rather there's a transition period between, say, these particular values, where there's a very fine line between whether you have effusive and explosive eruptions. And this is where we see the transitions, fast transitions between effusive and explosive eruptions. And you might have seen that in videos and studied about that, where you have fast transitions, perhaps on the order of minutes between fast changes between explosive and effusive eruptions at potentially dome eruptions, dome and volcano eruptions. So something like Seramu in Java in Indonesia is a good example of that. So what drives magma ascent? Well, really what drives magma ascent is how the magma degasses. So first of all, we have volatiles or gases dissolve within the magma, like here, kind of like a Coke bottle. Your Coke has those dissolved gases inside the magma. Then we start to exsolve those volatiles. Those volatiles start to come out of the magma and form bubbles. And it's those bubbles which make it really buoyant. So those bubbles, those volatiles, allow the magma to be dragged up to the surface and make it more buoyant and increase its magma ascent rate. And to the point where you get to those bubbles start to form networks together. And when they start to form networks together, they start to permeate out and those gases can be released. And those is something we call percolation threshold. So when you start to have these volatiles being released, they start to form these permeable networks. We can call this open system degassing. The volatiles are able to leave the system in an open fashion. The volatiles are decoupled from the magma. Whereas if the volatiles remain coupled to the magma, they don't connect with each other and they stay like this and they allow the magma to be dragged upwards very quickly, like our friend here. This is called closed system degassing. And I'll talk about this, these different processes a little bit later, but they drive different feedback mechanisms that can increase the ascent rate or decrease the ascent rate. So if you look at the literature for magma explosivity, volcano explosivity, you'll find that there's lots of different studies which show different things. There's lots of different contradictions. And one of those processes that does provide some contradictions is magma mixing. And this is where you have magma that's mixed just prior to an eruption. So, and this could occur, this could lead to either explosive or effusive activity, and I'll explain why. So if we have magma mixing, what this can sometimes do is it can flux in lots of volatiles. It can provide lots of volatiles to the system. It can provide heating and convection, and it can also increase the overpressure of the system. This can lead to explosive eruptions. Whereas sometimes we have magma mixing just prior to the eruptions, and this can be detected sometimes by monitoring networks. So for instance, of inflation of the system or lots of deep seismicity underneath the volcano. But sometimes this can lead to a reduction of viscosity. So this can reduce the viscosity, which lessens, as we just looked at before, lessens its ability to fragment into ash. If this recharged magma has little volatiles, then this can dilute the volatile content. And all of these processes can decrease the overpressure of the system and make this eruption effusive. So it's not clear at the moment whether magma mixing either causes explosive or effusive eruptions. We think it causes both. And it's probably dependent on several different factors, probably dependent on the extent of magma mixing, how much those magmas mix together, and how much the heat is transferred between them. The presence of exole volatiles, so in other words, those bubbles which are inside the magma, And also the time between you start mixing and the eventual eruption. So this obviously needs more study. But what we can learn from this magma mixing, and also lots of different other things, is that there's lots of different ways of causing explosive volcanism. There's not one way, and that's one of the messages I want to get out today. So here's a particular graph that I made, which shows that different kind of paths that you can lead. So in the deep system, you can have a magma injection trigger. As I said, this could either lead to explosive or effusive eruptions. We can see that if you have a magma injection trigger, this can lead to explosive eruption. If you don't have a magma injection trigger, this can also lead to an explosive eruption, often when it's at fast ascent rate. So in the mid system, or the sort of slightly deeper system, we can have fast magma ascent. Now, sometimes this will lead to explosive eruptions more often than not, but sometimes it won't. And sometimes there'll be external forces at play. So for instance, there could be phreatomagmatism, that's where magma interacts with water or with ice, or a simulation of carbonates into the system, like we might find at Merapi as well. And also we can have decompression waves. So that's in other ways, you take a system which has been decoupled from the top, so a collapse or a landslide like in Mount St. Helens, and that can produce an explosive eruption. And even without any of these processes, without a magma injection trigger, without fast ascent, and without any external forces, we can even, in some cases, form explosive eruptions. And now this is due to several different intricacies or complexities in the volcanic system. So one of these could be where the magma stalls in a dome system, for instance, stalls in the conduit, it starts degassing. And as it starts degassing, it starts to form crystals. And those crystals, as I said before in the introduction, they start to increase that magma viscosity. And as soon as you increase the magma viscosity, then you make those volatiles that drive explosive eruptions less able to be removed from the system. And this can lead to an explosive eruption. You can also, even if you exsolve those volatiles from the magma, they start to form those permeable networks out of the system, and they can leave the system. But sometimes they don't leave the system entirely, and they start to form underneath a plug. They start to accumulate. And if there's enough volatiles that start to accumulate underneath the plug, then those pressures can build up and form explosive eruptions. And this is really typical of volcanic eruptions that we see in Galeras, in Colima, Seramu, and lots of other places as well. So although there's lots of different ways of causing explosive eruptions, and there's lots of different factors that trigger either explosive and effusive eruptions, I want to try and bring it together a bit, because lots of that is complex and dependent on lots of different things. But what I'd like to say is that I think that you can boil these down to two main factors of what drives explosive or effusive eruptions. So it could be, it's very much dependent on how much the magma outgasses before the eruption, so it's outgassing efficiency, and also the magma ascent rate. And these two factors can explain a lot of volcanic behavior. So for instance, we can have rhyolitic lava flows here, rhyolitic compositions, and this inherently has a low outgassing efficiency. So because of its high viscosity, it's less likely to outgas those volatiles, and it can more likely lead to an explosive eruption. So that's why you have outgassing efficiency is low in this explosive regime over here, in this little triangle here, whereas the outgassing efficiency is high in the effusive regime generally. And we find the ascent rates are higher, which encourages a more explosive eruption, versus low ascent rates and higher outgassing efficiencies of the effusive regime over here. And you can see the transition between effusive and explosive is not a straight line, it's not a clear division, but it's this transition, which is this murky, unclear division where there's lots of different processes at work, but can sometimes be a fine margin between explosive and effusive activity. So as I said, more or lower viscosity magmas, things like andesites, will be much more likely to outgas their volatiles because of its lower viscosity, because of its less silicic magma composition. So what we're going to do now is we're going to plot on different ascent paths. So here's an example of one ascent path. I'm going to plot 3 more. So this is scenario A, where we start with a magma, which is stationary, so 0 is a magma ascent rate, and this undergoes closed system degassing. So this is just a reminder, this is where the magma and the volatiles remain coupled to the melt. And what this does is that it increases the magma ascent rate. And as you increase the magma ascent rate, going right on this diagram, you reduce the amount that that magma can release its volatiles. So it starts to form this magma path, and it gets faster and faster magma ascent rate. And that means that the magma is less able to outgas, and it can form a bottom-up Plinian eruption. So something like Calbuco here, or Chaiten rather. And once the magma loses its volatiles, it starts increasing its outgassing efficiency, then it can start to reduce its magma ascent rate, and it can become a lava flow after. Another example here is the difference between open system and closed system degassing. So open system degassing will normally lead to effusive eruptions, and that's because as the ascent rate increases, the outgassing efficiency increases as well. And this means that the magma is more able to release its volatiles, and this would normally, excuse me, send it into an effusive regime over here. But sometimes, and I mentioned these examples just before, sometimes that cannot happen. And this could be for a number of different factors. For instance, crystallization, which increases the viscosity, and that can decrease its outgassing efficiency, making it a more explosive eruption, sending it into the explosive regime. And then we can also have magma accumulating, or gases rather, accumulating underneath the plug, which can reduce its outgassing efficiency and sending it into an explosive regime. Once those gases are then released, then it increases its outgassing efficiency. It's able to degas and outgas, and then we can have slower magma ascent rate, and we can form more effusive eruptions. Then it can go in these different cycles, like you can see here, and that's what we see examples like in Montserrat. And then the last example over here is an example where we have a decompression wave Plinian eruption. And this is where, instead of example A, where the magma ascends from deep and then goes shallow, this is essentially the magma has already got to the surface. It might have ascended very slowly, it doesn't matter. But then what we have is we have an example where we have a flank collapse, like in Mount St. Helens, which then decompresses the magma and sends it very, very fast up to the surface. And this is where the decompression rate and magma ascent rate can be decoupled. So the magma can ascend slow, but then be completely decompressed very quickly. Another example of that is a recent example from Krakatoa in 2018, where we had this collapse, as you're very aware, I'm sure, in between Java and Sumatra, the collapse of the volcanic island, and that sent the eruption to be much more explosive, and that's because of that decompression effect. It released a lot of pressure and allowed the system to erupt much faster. And sadly, that really led to those fatalities in Java mostly, and led to explosive eruptions that we're still seeing some explosive eruptions today. And that's something we're actively looking at with Mirzam and the team at ITB with as well at the moment. So there's different eruptive style transitions that we find in the literature, and I talked about some already, but I want to talk to you about these transitions that can occur at different eruptive scales. So sometimes they can erupt in a single eruptive phase. So we could have dome growth and volcanic explosions that occur really quickly together. 1 minute you might have a lava flow, and then you might be punctuated by a very short volcanic explosion. And what we find is, actually, I compiled about all the eruptions which are volcanic explosivity index over 3 since the year 2000, of which there are 106 of them. And I looked through all the different reports and found that more than half, 61% of these, comprised both effusive and explosive activity. So more often than not, if you're seeing a major explosive or a major volcanic event, you're likely to see both effusive and explosive activities together. We can also have a different time scale altogether, and this could be at the same volcano over several different eruptions. So, for instance, one year you might have a lava flow or a lava dome, like a great example, and I'm going to speak to you briefly about this, is the Kelut volcanic eruptions. So in 2007, we had a lava dome eruption. And then a few years later, in 2014, we had an explosive plinning eruption. And this was separated by a repose interval. So I just want to make that distinction. There's sometimes these effusive and explosive transitions can be very close together, or they can be separated by a repose period. And what we can find by looking at the record of different eruptions from around the world, we can plot a graph like this. So this is the occurrence of the most explosive eruption within the lifetime of an eruptive period. So in other words, and this is the number of eruptions, just a histogram really. So in other words, if we have an eruption which has both dome eruptions and explosive eruptions, where does the most explosive eruption occur within the eruption phase? And we find that a third of the eruptions, a third of the most explosive eruptions, occur in the latter half of the eruptive period. So this is large explosions occurring during or after dome activity, which is really interesting. So it's quite unpredictable. But the majority, 70% in fact, of the most explosive eruptions within an effusive explosive eruptions occur in the first quarter of the eruptive period. So what we can say is that when we have those transitions within the same eruptive phase, is that these mostly go from explosive and then to effusive. So explosive, then effusive. But this isn't always the case. You can see that sometimes it ends up more explosive near the end. So this was thought at first, several decades ago, to be due to how much volatiles were in the magma. And that seems to make sense, because you would expect more volatiles, more water, more CO2 to be an impact on some eruptions. And in some eruptions, that is the case. But generally, it's more a case of a shift from closed to open system degassing. So that's what we talked about before, about that different change between a closed and an open system degassing. So this is what I'm talking about when I'm talking about open and closed system degassing. So in the open system degassing, as we talked about briefly before, these are volatiles which can become decoupled from the magma. That means that it can send you on this feedback loop, which can decrease the magma ascent rate and generally decrease the likelihood for an explosive eruptions. So volatiles are able to decouple from the magma. They're able to be released. This means that there's less exsolution, less bubble growth. You reduce the buoyancy and the overpressure, which can force the magma upwards. And by doing that, you slow the magma ascent rate. You allow more time for the magma to outgas. And that all allows more volatiles to decouple from the melt. And it generally leads to effusive eruptions. One in Kelut 2007. Whereas for closed system degassing, which generally increases the magma explosivity, the volatiles are coupled to the melt. So the volatiles are right there and they're not able to be released from the magma. This increases your buoyancy and your overpressure, things that allow the magma to be dragged up and increase the ascent rate. You can have nucleation, so the growth of small bubbles. And when you have smaller bubbles, lots of small bubbles together, this means that they're less likely to interact, to coalesce, and form those permeable pathways that allow the magma to outgas. So smaller bubbles mean that you limit your permeability. This allows the magma to ascend quickly, the decompression rate is quicker, and it allows less time for the magma to outgas. And this means that more volatiles remain coupled to the melt. So it goes round in this feedback system, as you can see here, that generally leads to more explosive eruptions. So I guess the question really is what leads to whether we have explosive or effusive eruptions, or in other words, why do we start with open system degassing or closed system degassing? I think that's a really important question that we're not really sure about at the moment, and that's something that I'm actively trying to research in my research at the moment. One of the ideas could be that the magma viscosity is changing at depth, and that could control things. That could control how much magma, magma or volatiles is outgassed before the ascent rate. Or it could be that the volatiles are changing as well underneath the magma. Or it could be that overpressure within the magma could be a factor in triggering whether we have open or closed system degassing. And this is what my research at the moment is all about, how to kind of forecast, if we can understand whether we have open system or closed system degassing and the factors that lead to that, that we might be able to help forecast eruptive style in the future. So we want to understand how those cycles start at depth in the magma reservoir. So what I do in a lot of my work is do petrological experiments and also study the petrology of minerals, such as this plagioclase here, which can tell us about the history of the magma as it grows from the core to the rim, kind of like your tree rings. And I'll talk a bit briefly about that in a second. And I also do these experiments. So this is my setup that I built in Oxford. And you can see I've got these furnaces here that allow the magma, little bits of rock, to be kind of put into the furnace, and they can be elevated to high pressures. And what we're trying to do here is to simulate conditions within the magma reservoir. So I aim to replicate those pre-eruptive conditions for flow and blow eruptions, explosive and effusive eruptions, and also understand what unrest signals, seismicity, deformation, gases, would these produce in monitoring data. And if we can do that, we can better forecast the eruptions. So just a few more slides left. And I'm going to talk to you about an example from Kelut volcano in Indonesia in East Java, and some of the constraints that we've done from experiments. So this is the eruption in 2014. And by doing lots of different experiments, by putting little bits of rock at the same temperatures and pressures and volatile contents in the magma, and doing lots of different experiments, we can estimate what the magmatic conditions were before that explosive and before the effusive eruptions. So in the explosive eruptions, so they had one in 2014, 1990, and various other ones. The temperature of the magma was about 1,000 degrees. The pressures were about 50 to 100 megapascals. So this is at a depth from about 2 to 4 kilometers. So quite shallow actually. And the XH2O, which is the fraction of water in the fluid phase. So in other words, the ratio between CO2 and water was 1. And that means that it's water saturated. So almost all the volatiles in the system were composed of water. And this is the kind of formula that I used. Whereas the effusive eruption in 2007 was at similar temperatures, maybe slightly hotter. So this is in the magma reservoir before it erupted. The pressure conditions were exactly the same, so it likely utilized the same magma body at depth. But the big difference is that the water, the volatile contents were slightly different. In this instance, there was more CO2 in this magma than there was in this magma. So the water fraction was about 0.5 for this effusive eruption. And the reason why we think that could have an effect is that because if you have more CO2, this means that CO2 has a lower solubility, particularly at depth. So it dissolves more early, and this means that there's less potential to drive that degassing-induced magma ascent that we talked about at the start. So more CO2, less water in this instance, not all instances, meant that there was less potential for fast magma ascent. And we also, in a separate study, looked at the analytical petrology. So we looked at these crystals, as you can see here, this plagioclase phenocryst that showed these zones of different growth as the magma grew. And what we found is that within the magma, and this is an example of the chemistry of the crystal, we can see that it goes from different regimes. It goes up and down. We measured the chemistry of the mineral, the magma, in melt inclusions and also in the crystal, and also the volatile contents as well of the water contents rather of the melt inclusions. And what it shows is that the magma goes through different periods. Sometimes it is cold and water rich, and sometimes it's hot and water poor. So it goes through these different undulations, which is really interesting. And if we can work out we calculated the viscosity, this effect that had the cold and water rich cycles had, and the hot and water poor cycles had. So, and what it shows, and this is the viscosity down here, and this is the magma growing from the start till the end, so right before the 2014 eruption. And we can see that during the recharge of magma, where it was hot and water poor, which we think was associated with magma recharge into the system, this decreased the viscosity quite significantly. Whereas as we cooled the magma, this made the magma more viscous, and as we differentiate the magma, make it more water content rich, then this also decreases the magma, but not as much as the decrease from the temperature. So what we find just before the 2014 explosive eruption at Kalut is the magma was really high viscosity comparatively, and was also water saturated before the magma. And this means that we think that this allowed the magma to be at a closed system degassing regime. So the volatiles were unable to be released from the system because the magma was a high viscosity, and there was lots of volatiles decompressing within the magma because we find this water saturated magma, as we showed in the experiments. Where we had the 2007 eruption, where we think the eruption was before the 2007 eruption, we think it was caused by a magma injection trigger. This means that this was a hot and water poor magma. This means that it was lower viscosity and water undersaturated, so more CO2 in the magma. And this means that this CO2 outgasses earlier, and it's more able to outgas because the viscosity is lower. And this led to these open system degassing regime that led to more effusive eruption. So just to summarize really, and I want to say that, as I showed before, that there's different mechanisms that can lead to either explosive or effusive behavior. And I showed that diagram there, and all of those figures are in my papers, and you can check those out. And we saw transitions on different length scales, sometimes in a very short time period and sometimes separated by a repose interval. And these seem to be driven by changes in open system and closed system degassing at depth. And their feedbacks, as we showed, those feedback cycles involved things like the magma ascent rate and also how able it was to outgas, its efficiency. I think that explosive Plinian eruptions, the ones that are driven from the bottom up, are the least well understood, and we need to do a lot more research into these. And that's one of that's one of the eruptions that I want to look at, is these explosive Plinian eruptions. And I feel like we need to do more research into poorly constrained factors that we're not sure yet trigger either open system or closed system degassing regime. So I feel like there's lots still to learn in this particular science. And the ways to look at this that I think might be the most beneficial could be understanding the pre-eruptive magma state, how the overpressure of the magma conditions before the eruption, how the volatiles behave, and how those volatiles are able to outgas. So thank you so much for your attention. And obviously I went through a lot of different things, but if you have any questions or want me to explain anything in more detail, then I'm happy to do that. Thank you very much. Terima kasih.
Terima kasih. Thank you very much. My very interesting talk about the explosivity of a volcano. We already four questions from the audience. The first question from Mr. Alexander. Maybe he will ask you directly. But before he asks, maybe I would like to inform you that that our student who take volcanology class in this semester also join with your.
Oh, good.
Yeah. So I asked them to give you some question or maybe some notes maybe. Cool. Okay, from Pak Alexander, maybe you can ask directly to Mike. Yes, please.
Okay. Thank you, Mr. Isam. Hi, Mike.
Hi,
my name is Alex Elake. I'm from the Physics Department of Patmura University. I want to ask you about almost all of the volcanic data you display is volcanoes on land or a volcanic island on the surface. I just want to ask you about how about the volcanoes under the sea? Because in Maluku area, we know that we have the volcano under the sea. I want to know about both of the eruption information, the length of time, the pre-eruption activity, and the type of eruption about the volcano under the sea. Thank you, Mike.
Thanks, Alexander. Yeah, it was really good question. So I have mainly in my research been looking at volcanoes on land. And those are either on land, so in the middle of the USA, for instance, or they can be on islands. And that's very similar, the systems themselves. So that's what I've been mainly constant, and that's what the talk was mainly based on. But you're right that there's lots of hazards from volcanoes that occur under the sea. And sometimes they're harder to measure, right? They're harder to, as you said, to monitor with seismicity or see how they deform or gases. So that certainly are a risk. I would say sometimes it depends on what depth those magmas or those volcanoes are. If they're very shallow underneath the sea, so in instance we have Krakatoa in the 1920s, and there was lots of different submarine eruptions, and they were slowly getting the volcanic edifice was slowly growing towards the surface, and as it got closer towards the surface, it meant that there was less pressure on the system, and also there was you were able to entrain air, and there wasn't too much water suppressing the magma and suppressing the volcano. So sometimes when they're very shallow, say below 100 meters, below 200 meters of water depth, then those can still have very explosive eruptions. And sometimes these kind of Circean eruptions or Phreato-Plinian eruptions, and those that we can see in Krakatoa recently in the last few years. Some of those eruptions have been very shallow, but still underwater. But with very shallow depths, they can still have very explosive eruptions. For those volcanoes that are very deep, then they are less likely to be explosive. And that's because the depth or the mass of water on top will form a lot of pressure on top of the edifice, on top of the volcano. And that means that the gases that drive the magma that are very much dependent on pressure are less likely to exsolve and to make the magma ascend very fast. But then, you know, there's always exceptions in the natural system, and there's also exceptions in the submarine system as well. And sometimes we do have more explosive eruptions. An example of that, sometimes the ones in Tonga and New Zealand, just north of New Zealand, that we found kind of rhyolite eruptions. And what these do is form these kind of pumice rafts. Sometimes we don't even know that they're going on, but then a few days later we might see on ships that these really massive pumice rafts, and obviously they can have implications for shipping and things like that. And also sometimes submarine explosive eruptions generally don't have less impact in terms of danger to life, but sometimes if they produce big belches of gases, then those can lower the density of anything in the water above. So if there's a ship just going above a volcano which is outgassing violently, then that can cause the ship to sink.
Thank you, Mike. That's give me the explanation about how the volcano under the sea activity. So I think we have so many topic for that. That's the good example for our student to studying about the volcano under the sea, because in Moluccas area, in Moluccas, we know that we have more than 2 or 3 mountain volcano under the sea. So it's good. For example, in Ambon, in Ambon, we have the manifestation about the volcano in the Latu Halat. There is the rest of the lava there. So maybe it's good for our student to study about the chemical parameter or the physical parameter about the lava in Ambon Island. Thank you, Mike. Thank you. Thank you, Mr. Rizal.
Thank you, Alexander.
Thank you, Alexander. So you can hear, Mike, that this is something like a sign or friendly invitation that you should come to Ambon from Alexander and also from the president of the university. Because near Ambon, there is a Banda Api volcano located in the middle of the Banda Sea, but very different character with Krakatau. So maybe someday we should visit Banda Api.
Sounds
okay,
good.
And then the next question is from our student from Fikri. Fikri has two questions. The first question is how to identify whether a volcano has an open system or closed system. Open or closed system. And then is there any relationship between overpressure with the type of the volcanic system, open or closed?
Yeah, so both really interesting questions, and I think this is exactly, Vikri's kind of identified exactly where we need to study more and exactly where I think that concentrations should be concentrated. And that's something that with my PhD students, I'm looking at in more detail. So how to tell whether a system is open or closed is a really good question. I think to some degree, you can look to see if the gases are being completely stopped at the surface. So sometimes you might be able to see the gases being released in plumes, and sometimes that can just be shut down, and that might mean that the system is closing up. And I'm also looking at potentially the ratios of different volatiles like the halogens, chlorine, fluorine, bromine, as a way to tell between open and closed system degassing and if the magma is cooling or becoming more water saturated. So I don't have a good answer for the first question. There's not a lot of good indications of how we can tell whether the magma system is open or closed system at depth. But this is something we should really focus on. The second question about overpressure is really important, and the question was, how does it affect the open versus closed system? Is that right? Yeah. So
yes, sir.
Yeah. So what we think is that overpressure is really able to be generated, so high amounts of overpressure are able to be generated when we have a system which is more closed. But it can be either generally. But generally, if the system is open, then the volatiles can be released, and it's less likely to generate those overpressures.
Okay. I think still related to this question, and then the other student asked about how about the product if one volcano has open system and another volcano has a closed system. In terms of the product, is it similar or different?
Yeah, in terms of the product, very similar. So in terms of the magma chemistry or lots of different factors, it looks very, very similar. So it's very, very hard to tell apart if they were open or closed system degassing. Almost the way to tell if they're open or closed system mostly is whether they have erupted effusively or explosively. So if the system is open, then generally the magma will be, the glass in the magma will be free of volatiles because it's all erupted, all left the system. If the magma is closed, then the volatiles might be more inside the magma. But generally those closed system magmas will be the ones that produce explosive eruptions. So you might find bubbles kind of stuck in pumice and things like that.
Okay, Mike, thank you. This very so many questions from our students indicating good condition, yeah, for volcanology in the future. And then the next question from Ellen. Ellen, maybe you can ask directly to Mike. Zeppelin.
Thank you, sir.
Yes.
I have two questions. First, does the shape of the volcano itself can affect the type of its eruption? If so, is the formation of caldera affects the type of eruption, or can it triggers the transition from, for example, explosive into effusive eruption and vice versa? Thank you.
Oh, yeah, thanks, Zeppelin. Yeah, so yeah, that's a really interesting question. So the shape of the volcano doesn't really affect, we think, the effusive or explosive regime. And as I was saying, it's more dependent on how fast that magma ascends and how kind of able it is to outgas beforehand. So that's independent mostly from the shape of the volcano. And the shape of the volcano sometimes is a consequence of those factors. So if you have a volcano or a magma that ascends really quickly and there's a lot of magma and it's not able to outgas, then those will form really explosive eruptions, form big craters, form calderas. And so it's really the style of the eruption that shapes the volcano. But, and your kind of second part of the question really alludes to this and is a really good question, is that sometimes if you have, during that process of eruption, things like the shape of the volcano can make an influence, because if you have a big system, which is a big, say, stratovolcano, you start to form explosive eruption because of all those different factors that we talked about: fast ascent rate, low outgassing efficiency, closed system degassing, and it forms an explosive eruption. And then sometimes it can remove all of the overburden, so it can remove the edifice itself and form this big crater. And because you have less weight on the volcano on the surface, then that during the eruption, that can increase the explosivity because it causes more decompression. So this is kind of like what happens in big caldera eruptions. So it's what we're finding with PhD student of mine, Amber, that also Mirzam also kind of supervises and helps out with, looking at Krakatoa, the 1883 eruption, is that we saw initial and explosive eruption, but then as that explosive eruption started occurring, and that explosive eruption occurred over the course of several months, as the magma started decompressing at depth, it started destroying the edifice above it, forming this caldera. And as you form that caldera, what that does is it causes the whole magma underneath it that hasn't been erupted to release all its pressure at once, like Mount St. Helens. and that can form even more explosive eruptions. So it can change the volcanic shape as it changes through the eruption, can change the eruptive style as well. Hope that answered your question.
Thank you so much, sir.
Okay, Lynn, thank you very much for your question. We have the last two questions from Excel. You can ask directly maybe to Mike. Excel.
I'm sorry, sir. Maybe can you hear me, because in where I live there's a heavy rain, so it affects the signal a little bit.
Yeah, I can just about hear you.
Yeah, okay.
Oh, okay. My question is, does the stress direction from the activities of the seismic affects the ascending of the magma, so it can determine the type of explosive of the volcano, especially on the open system or the closed system of the magma? Thank you, sir.
Yeah, that's an interesting one. I think we don't really know that so much yet in terms of how earthquakes affect the style of the eruptions, but I think it's an important one. I think it can do both. I think in order to the stress regime in particular does have an influence on how fast the magma can ascend. Sometimes if there's a kind of a high stress on particular regions, then that can make the magma ascend faster or slower. And then the seismicity, so if there's an earthquake before and then that causes an eruption, so we're not sure whether those cause eruptions, but sometimes if the magma is just ready to erupt, then in those instances we think that sometimes an earthquake can trigger an eruption. So it's certainly not all the time. There doesn't seem to be there's not much data on this, but there doesn't seem to be much influence on the eruptive style that an earthquake occurs. Theoretically, I guess you could say that it could do both. So it could, this dynamic stress changes and shaking that an earthquake would produce could allow the volatiles to go into coalesce and to form those permeable networks and produce an open system degassing. So that could reduce the likelihood of an explosive eruption. So that'd be my guess, that it might reduce the explosivity, but something to study, definitely.
Okay, Mike, thank you. Yeah, exciting. Yeah, you can learn from the example from the last earthquake that we have in Lombok. There are several big earthquakes, but there is no response from Rinjani volcano. But in the other case, from Fuji, in the 17th century, there is strong relation between earthquake and also the activity of Fuji. Okay, thank you, Mike. And then the last question from Saskia. Saskia is still there?
Yes, sir.
Okay, yeah. You can ask.
Thank you, sir. I have one question, and my question is, if an effusive volcano turns into explosive volcano, what is the best mitigation system to deal with it? Thank you, sir.
Yeah, it's a really important question. Thanks, Saskia. It's difficult. So we are, so right at the end of so I wrote a review on this subject about explosive and effusive activity in Nature Communications. And at the end of that review, we talked about what could be the best ways of telling when we're going to have an explosive eruption or an effusive eruption. And I think looking at examples from, say, Merapi or Pinatubo, and examples where we've seen these kind of Merapi in 2010, for instance, and lots of other different eruptions. What we can say, I think, is that in explosive eruptions, we see a faster ramp up of activity than effusive eruptions. So in other words, in effusive eruption, we might have seismicity rumbling along for a long time, slowly. But in explosive eruptions, we see kind of sharp changes and faster exponential kind of growth of seismicity. That seems to be the case, certainly for the Kelu eruption that I looked at, that had seismicity only in the last kind of high seismicity only in the last few weeks before the eruption, before the explosive eruption. Whereas before the effusive eruption, we had kind of 4 months of deep and shallow seismicity and outgassing and other things like that. So generally, effusive eruptions have more warning and slower ramp up, and we find that there's more indicators of unrest at faster rates before explosive eruptions. So it really means we need to be really kind of on guard or on alert when we start seeing these fast increases of different monitoring criteria. So increases in deformation, fast increases of seismicity, gases, etc. When those all occur together, like they did in Merapi, 2010, etc., then those can initiate the fact that we might be seeing magma ascending more quickly, or something happen in the system more quickly.
Okay, thank you, Mike. Yeah.
Thanks, Saskia.
Okay, thank you, Saskia. And then I just summarized some question from YouTube. The first question is related to the explosive eruption under deep water. I think you already mentioned and explained. And then the second question is weathering product of volcanic glass. So you can explain the relation between weathering product with the halogen.
With halogens, is it?
Yeah, halogen. Yeah.
Yeah, that's something I'm trying to do at the moment. Actually, is I'm measuring halogens, so chlorine, bromine, and fluorine in volcanic glasses and experimental glasses. And trying to understand at what pressures, temperatures, and water contents and things like that, they start to either go into the gaseous phase or retain or stay in the melt. And if we know that, then that can tell us potentially if the magma, we can measure those at the surface in a volcanic plume, so like hydrogen bromide or hydrofluoric acid, etc., coming out the plume. And if it decreases or increases, then that might give us an indication of if the magma is cooling, or if the magma is increasing in its water saturation, and things like that. So that's a potential area for more study at the moment that I'm looking into.
Okay. Okay, thank you, Mike. Yeah, I guess we still have many questions, but our time is limited. So maybe before we close the session, last question maybe from the lecturer or from the president of the university, or from the Pak Piko, maybe Pak Edi.
I have no question.
No question. Okay, Mike. Maybe I have one question. How about the possibility of the student from University of Patimoras to study in Oxford University?
Yeah, so I think this is, we would love to have students over. There's problems that the UK government and the university make it very expensive for foreign students. And that's a real shame for people like myself that really want to kind of have more connections with universities in different countries. And the best way really is to apply for scholarships in your home country in Indonesia. And and obviously I can help support that at my end, but that's the best way of coming to Oxford or the UK. Scholarships from their own country.
Okay, Mike. Thank you very much. I think this is a good sign and also good information. As long we have our own funding, maybe we can go to study in Oxford.
Yeah.
Okay, thank you very much for your Mike, for very nice presentation, and thank you very much for the audience for the time. So before we close the session, we should have a photo session. So would you please turn on the video for the audience and our participant? Okay, I will take picture. 1, 2, 3. 1, 2, 3. 1, 2, 3. Okay, thank you very much. So, Pak Rektor, would you please to give a closing ceremony? Pak Viko?
Ya, baik. Pak, kedengaran ya Pak?
Kedengaran, silakan.
Pak, ini ya Pak Rektor, tadi ada masalah sedikit, jadi
Oke.
balik. Ya, mohon sebentar Pak.
Baik. If the students still have questions, is it possible to send you email, Ma?
Yeah, sure. Yeah, sure.
Yeah, okay. Thank you. We are still waiting for the rector to rejoin.
Sudah?
Oh, okay.
Belum masuk.
Yeah.
Belum masuk. Langsung klik link saja. Klik linknya saja. Oke. Belum.
How is everything in Bandung, Mizan?
Sorry?
How is everything in Bandung?
In Bandung, everything is okay. Yeah.
Oh, good.
Yeah, the weather is very nice, but problem only COVID-19.
Okay.
Yeah, so our university is still closed.
Oh, is it? Oh, wow.
Yeah.
Yeah. So same here. Our university is pretty much closed. Yeah.
And always extended. Actually, the last time it was the 12th of June, but because the condition is not that good, so it is extended again with the 14 days until the 26th. I don't know after that. But, probably the institute or the campus will be open, but that's for the young. For me, because, I'm above 60, so I have to work from home anytime. Mirsam can enter the campus. He's still young.
And how about in UK? I heard that the campus will be suspended until next summer.
Yeah, I don't know. We don't know at the moment. Certainly, there's not much. Some people are able to go into labs at the moment, but not many, and not a lot of lab work. So generally, we're all working at home, and maybe it's a few months before it opens properly, or maybe longer. I don't know. But,
okay.
See.
Maaf, masih di mute Pak Viko. Bisa di unmute dulu Pak Viko.
Enggak, menunggu Pak Rektor kayaknya.
Iya.
Masih Pak, ada masalah teknis sebentar. Mohon maaf.
Oh, iya, oke. So we are still waiting director to rejoin.
There was a question here from Indri about if it's possible that the volcano has two kinds of system, and if it's the product of magma mixing.
Iya.
Oke. Pak Rektor sudah ada
Really? Oke.
menggunakan Ibu Wilma punya
different computer. Okay, Pak Rektor, welcome back to the room. I know we are at the end of the session, so would you please give a closing remark to our guest lecture? So I will open. Please unmute, please. Bu Wilma bisa dibantu unmute, Bu Wilma? Oh, sudah ya. Oke. Iya.
Sudah, Pak. Yeah. Thank you very much, Dr. Mike, for your good presentation. And I think it's very important for lecturer and student in Pak Timur University. And I hope the next time you can participate with our in Pak Timur University. On behalf of Pak Timur University, I would like to thank you very much for your participation. And I think the next time I invite you to Ambon for lecture in Pak Timur University. Thank you very much, Mike, and gratitude for your family.
Thank you very much. Yeah, terima kasih to everyone, and yeah, thank you.
After COVID, I invite you to Pak Timur University. Thank you, Pak Dr. Rizab dan Profesor Edi dan teman-teman sekalian. Terima kasih
Dengan
atas
senang hati, Pak.
partisipasinya. Pak Edi, cepat-cepat COVID selesai, kita ke Bandung,
Amin,
ke Ambon,
amin,
karena
Pak Beda, Pak Beda.
Fakultas baru tuh Pak Edi.
Iya. Ini saya di Ambon loh, itu di dekat gedung Rusia itu saya.
Ya, kita sudah dapat gedung baru Pak untuk prodi ini, tapi kalau mereka mau lulus ini bagaimana nih Pak, tidak ada fakultas baru. Jadi kita mau buru fakultas itu Pak.
Iya.
Karena sudah 3 tahun, 4 tahun ini mereka harus punya ijazah dengan pimpinan fakultas Pak.
Iya.
Baik Pak Rektor, Bapak Ibu sekalian, thank you very much Pak Rektor, and also all the audience. Mike, once again, thank you very much for your time, also for your coming in this session. And I would like to say, see you in our guest lecture in Empati.
Thank you. Yeah, Mike,
Thank you very much. Yeah, nice to meet you.